Hello, everyone. My name is Han Wang. Today, I'm going to talk about the parameter tuning problems and how to make them distributed using Spark and Fugue. I will give a brief introduction of the tuning problems and how we categorize them. Then I will go through the common algorithms for non-iterative problems. And in the demo, I'm going to show how to do hybrid searches using the tune package. After that, I will go through the common algorithms for iterative problems. And in the demo, I will show how to make these algorithms work on Spark using Tune and Fugue. Today's focus will be Tune, an abstraction layer for parameter tuning. It relies on Fugue and Spark to achieve its functionality, but it encapsulates most of the complexities. So for many use cases, you may not need to know Spark or Fugue at all. Please notice that both Tune and Fugue are open sourced, and you can directly pip install both of them. Let's start. Here are some common questions or confusions about parameter tuning. Is this a machine learning problem? Are there common ways for tuning? Why is it so hard to leverage a distributed framework to do parameter tuning? So assume this is general parameter tuning problem. For machine learning, we call it hyperparameter tuning, and it is a subproblem of the general problem. Inside machine learning, we have classical models and deep learning models. Both need tuning. So assume this is general parameter tuning problem. For machine learning, we call it hyperparameter tuning, and it is a subproblem of the general problem. Inside machine learning, we have classical models and deep learning models. Both need tuning. Well, let's take a step back. Let's categorize the general tuning problems in another way. Non-iterative problems refer to the objective that will run just once to get a metric, then stop. Iterative problems refer to the objectives will run multiple iterations, and in each iteration, it will generate a metric. If we categorize in this way, we find tuning for most classical models are non-iterative problems. And the tuning for all deep learning models can be considered as iterative problems. And some classical models, such as boosted decision tree, can be treated as either one. With different categories, let's see why distributed parameter tuning is so hard. First of all, obviously, not everything can be parallelized. Iterative problems count, and some search algorithms have to be sequential too. Secondly, to tune even the simplest problems, you have to describe the searching space, define the objective, care about distributed worker status, how to collect results, how to prune. It seems you have to define everything. Popular tuning frameworks initially do not consider distributed cases. So later on, the design for distributed cases becomes awkward and complicated for normal users. Ray-tune may be an exception, but it's locked with Ray, not as popular as Spark. Spark is not designed for tuning particularly. For iterative problems, real-time asynchronous communication becomes the biggest challenge. It does not even align with Spark's design philosophy. Now let's talk about how we build abstraction layers to help solve these challenges. There are different computing frameworks, Spark, Dask, Pandas, and on GPU, Rapids, and Blazing SQL. Fugue is an abstraction layer unifying the computation. On top of Fugue, we already have Fugue SQL and validation. They are not today's topic. On the other hand, there are existing hyperparameter optimization tools such as HyperOPT and Opportuna. The Tune framework is built upon Fugue and existing HPO tools. It redefines the space concept and adapts to the HPO frameworks, and also leverage Fugue for distributed computing. So for users, they only need to use a small set of unified APIs to interact with all the great underlying frameworks and to switch freely. Here are the high-level goals for the Tune framework. For non-iterative problems, we unify grid and random search, and for all other algos, we make them pluggable. For iterative problems, we generalize state-of-the-art algorithms such as Hyperband and Asynchronous Successive Halving, bring them to all execution engines Fugue supports, so users will have much higher flexibility to configure their search. For both, we will make the search execution seamless between local and distributed environment. Tuning is difficult, so we make the development iterable and testable. We minimize the moving parts. We don't need a database or a queue or array on Spark. We minimize the interface. For majority use cases, you only do single API calls, and Spark and Fugue are totally hidden from you. Now let's talk about non-iterative problems. Grid search is probably the most commonly used tuning method. It is straightforward, cross-product all choices on all parameters to get all combinations. It's deterministic and can cover each value of a parameter with equal probability. But the search space size for complex problems can be very large and sometimes unnecessary. Random search relies on how many samples needed from a search space. So we can control the size of the compute. And it is also great for continuous variables. However, it may not be deterministic. And for complex problems, we still need large sample size to cover combinations. Bayesian optimization is one of the advanced searching algorithms. The search starts with random guesses, but for each step, it takes into account the previous search results. So the guesses will be more reasonable and faster to converge. It normally takes much less compute size to achieve the comparable result compared with random and grid search. However, due to the nature of the algorithm, it has to be sequential. So it's not necessarily faster than grid and random searches when you have a distributed system. None of the algorithms is perfect. The best way is to flexibly combine them together as a single search task. In order to do that, we redefine the concept of space. We treat grid search and random search as the first level optimization, in which they simply provide a collection of configurations. And we parallelize on this collection of configurations. And we treat all other algorithms, such as Bayesian optimization, as second level optimization on each of the configuration. And we can plug in third-party solutions for the second level optimization. Here is an example. This search contains model sweeping, grid search, random search, and Bayesian optimization. Grid and random configurations are generated before execution, and Bayesian optimization is done in the runtime. Now let's discuss the iterative problems, and we are going to use Keras model tuning as our examples. And because Kaggle machine is now so powerful, we are going to use the Boston housing data set in this example. And if you have ever trained a deep learning model, you will know that it is more complex than the classical models. You have to implement different things for a deep learning model. For example, you have to construct a model, you have to care about how to compile it, how to fit it, and how to handle the output metric. And so in order to make it more organized, we create a Keras training spec template class. And this class does not really add anything, but just to help you reorganize your Keras training code. Now let's go through the logic. For the initialization, we can consume the data frame from the data frames passing by the distributed system. Or on the other hand, in this case, we just load the data from the Keras datasets. And for constructing model, we build two dense layers. And for the first level, we set the number of cells to be L1, and L2 is the number of cells for the second layer. Our objective is to optimize L1 and L2 in order to produce the best validation metric. And for compile, we have specified our final metric. What we care is the mean absolute error. And here for the fit metric, this is how we get the mean absolute error from the validation set. And also for sort metric, so notice that for Keras output, the metrics can be larger better or smaller better, but for sort metric, it must be smaller better. For errors, we can just return the original metric, but if it is accuracy, then we need to return the negative value of the metric. With this training spec, we are able to do hyperparameter tuning for the Keras models. But before tuning, it will be great if we can validate everything we have implemented here is working locally. So here is how we do that. We just give some dummy hyperparameters and data frames. And then we just call this function, compute sort metric. This function is designed for testing purpose. It will for sure cover everything you have written here and to generate the final sort metric. It is an end-to-end execution that is very similar to the execution of a single run. Now let's run it. As you can see, the result is not good, but that doesn't matter. The thing we care is if it can run smoothly from end to end. And it seems it's working. Deep learning training is very expensive, so it's better to do validations as early as we can, before we use a lot of compute resource to do expensive jobs. Okay, so now we have validated that our training spec is working as expected. Now let's just import the utility functions for Keras model tuning. It is very similar to how we tune the secular models. Okay, now let's start with the simplest case for Keras model tuning. First of all, we just need to define the space, right? Space equal to Keras space and housing spec L1. Let's do a random search. Okay, so we want ran int from 8 to 32. And L2 rand int from 8 232. So this is our space. And how can we run the simplest successive halving? We just need to do this. We need the space and we need a plan. You remember we talked in the slides, we need a plan for reducing the candidates and how many epochs to run. So let's try the simplest one. 2, 0, and 1. So this means for all the candidates from space, we will run 2 epochs, and then I will select just one of them to promote. Because we have only one run, this one result will be the final result. And also, I forgot one thing, which is we need to make this a random search space, so we need a sample. Let's use 16. Okay, so this is everything you need to do a successive halving on top of a Keras model, if you just want to do things locally. And we can do an additional thing is we can set restricted top to just 2 values, right? And in the end, we just output the results, print the results here. So as you can see, actually, we also think this is another type of validation after this validation. This validation has no knowledge of tuning, and this is the simplest tuning case. So you can see that we are able to validate things locally, step by step, and to get the best result. As you can see, even with this type of simple run, we get much better result than the previous one, right? Okay, so now let's run a more traditional successive halving. As you can see that for the traditional successive halving, we increase the epochs by the factor of 2, and we reduce the number of remaining candidates by the factor of 2. This is a lot of compute, so we'll see that it will take a while to finish. And now let's think about, it's a lot of compute. How can we bring this to Spark? So again, it's just like before. We only need to specify the execution engine equal to Spark. And because of Fugue, this Spark is a shortcut to start a local Spark cluster on Kaggle. Oh, as you can see, the previous result is already here. It's pretty good. It's much better than the simple plan. This traditional plan is great. Okay, now this is the way we can run things on top of Spark. And there is another thing. What if we also want to do real-time monitoring? And again, it's just like before. We only need to enable the callback for this execution engine. And we tell the system we want to monitor runs. Let's see what will happen here. So here, we will monitor for each trial. We will just have the metrics for each runs. And here we just plot all the trials we have collected so far. So it is a typical chart. You will see a typical pattern for successive halving in real time. It's a live show. And as you can see that for each run, we reduce the number of candidates to half. So you see less, less, and less. And finally, we get a result, right? So this is how successive halving is working. We visualized it. Okay, so what if we want to do Hyperband? As I have said, the Hyperband is just to run a collection of plans. So we only need to change the plan to plans, and each one is successive halving like, right? And also we can increase the number of samples because there are more searches, so it's better to feed the system with more samples here. And all other things will be the same. And another thing I want to mention is that the monitor, although we have a shortcut here, you can fully customize the monitor by implementing the monitor class. You can connect this system with MLflow. You can push all the metrics to MLflow to visualize or to save. As you can see, the Hyperband is quite similar to Successive Halving. But it will just try more things, because we have a collection of plants. These 24 samples will be assigned proportionally to all these plants. Okay, now what if we want to do continuous or synchronous successive halving? Again, you only need to change this function, and then let's change back the plan to a single array. As you can see, we have a warm-up here. So we can set warm-up. You can set warm-up for any of these three algorithms. It makes more sense to set warm-up for asynchronous successive halving and successive halving. For Hyperband itself, it has some warm-up idea already, so probably it's not necessary. And also, I need to mention that practically for continuous asynchronous successive halving, it is way more efficient than the other two algorithms. So here you can sample way more candidates for it to start. Now let's talk about iterative problems. The most typical examples are deep learning models tuning. Solving iterative problems is all about how to quickly stop the bad experiments and move compute resource to the promising ones. So the first challenge is how to do early stopping. If for each configuration and each iteration, it tries to get an immediate decision, then different trials will need to communicate in real time asynchronously. How can we make this happen on traditional distributed frameworks such as Spark? If for each configuration and each iteration, we use checkpoint and file system, then the overhead of saving and loading and idling can cause inefficiency, especially when you have a large compute resource. Other challenges include each single problem can't be parallelized, and a lot of boilerplate code to make it work on any framework. Now let's quickly go through some well-known early stopping algorithms. The most basic one is successive halving. In this particular case, we start with 8 configurations, either randomly generated or specified by user. Then after running 1 epoch, we keep the top 4. Then run 2 epochs, keep 2. Then run 4 epochs, keep 1. In the end, we run 8 epochs on this configuration to get the final model. We can use the initial number of trials, initial number of epochs, and a factor for reduction to describe the traditional successive halving. And in this case, it is 8, 1, 2. But in my opinion, this problem is oversimplified. In our framework, you can fully customize the process with number of trials and the number of epochs in each run. Here is an example. We start with 8 configurations, run 4 epochs, keep 6, run 2 epochs, keep 2, run 6 epochs, keep 1. With this design, the traditional successive halving is just an array of tuples. And even with warm-up, it is still an array of tuples. And you can invent your own array. Hyperband is roughly a grid search of successive halving. For a single successive halving, if it runs just one epoch to discard candidates, it could be too early. But if it runs full epochs to discard candidates, it could be a waste. So Hyperband is to try different starting points while keeping each attempt using roughly the same amount of compute resource. And again, we have generalized Hyperband to be an array of tuples. The traditional one is just a special case. You can also invent your own arrays. No need to follow the original formula. Asynchronous successive halving is a big improvement over successive halving based on a simple idea. If we have 8 workers for each run, each worker does not wait for all others to finish the same run, but just to compare itself with the already finished ones and decide whether to promote to the next run or to stop the current configuration and pick up a new configuration to start over. So we will see a few things. 1, trials finished earlier will have higher chance to get promoted. 2, all workers keep busy without waiting. 3, great trials will be promoted to the end, even if early trials have reached the end. So the final result is still good. There are definitely wastes in this case, but practically speaking, the utilization of compute resource is much higher, and this is more important. As you can see that asynchronous successive halving will never wait for other runs. It will just, any worker will just get promoted or get killed in real time. And the continuous successive asynchronous successive halving means that we do not do any checkpoint. So for the other 2 algorithms, we always rely on checkpoint. We save the models to disk, wait, retrieve the model, and continue the training. But for continuous asynchronous successive halving, we don't checkpoint any of the training during the process. For each end of the run, the worker will just ask the driver, should I continue on this trial or should I just quit and start with a totally new trial? And it will get a decision immediately. So it does not have to checkpoint anything in this case. And as you can see that the result is also a little bit better than the other 2 algorithms. Actually, I didn't show the time. So practically speaking, if you have a lot of compute resource, asynchronous successive halving will outperform Hyperband and successive halving on almost everything. The speed, the cost, and the quality of the output model. But if you have very limited resource, for example, you have only one machine, you can only train the models on your local machine using a single GPU, then probably Hyperband and successive halving, they are the better choices for you. And for those cases, you just remove this execution engine to run everything using the single GPU. To sum up, Tune is an abstraction layer unifying the core concepts for parameter optimization. We divide it into non-iterative and iterative problems. And based on the 2 categories, we're working on specialized solutions for all popular machine learning frameworks. Our goal is to provide non-invasive and minimal functional APIs for all major tuning scenarios. And the scientists will be able to do tuning without requiring the knowledge of distributed systems. Meanwhile, we will enable advanced users to create fully customized and platform-agnostic and skill-agnostic tuning pipelines using our lower-level APIs. Please let us know if you are interested in collaborating with us to democratize distributed tuning. Thank you.